This is an introductory exercise on calculating a differential equation solution in Excel. We're going to take two different methods for calculating this. The first one is going to be an analytic solution to this equation, and the second one is going to be a numeric solution. So the analytic solution is by either separating and integrating. You can also use Laplace variables to do this. Let's just go ahead and review that. Okay, we have this differential equation right here. We're going to separate, so we're going to put all of the CA terms on one side and all of the time terms on the other side of this equation. So I have dCA divided by CA, and that's going to equal negative k, which is a constant, times dt. So we separate and then we integrate. So we're going to integrate from t1 to t2. Okay, just arbitrary time, and going from CA1 to CA2. Let me erase those. Okay, so we have our analytic solution by integrating this. Let's keep going off to the right here. So this is going to be natural log of CA, and we're going to evaluate this at the limits CA2 to CA1, and then we also have negative k times t, and we'll evaluate that from t1 to t2. Okay, next step is that we have natural log of CA2 minus natural log of CA1. This right here is going to be natural log of CA2 divided by CA1, and that equals negative k times t2 minus t1. We're going to call this delta time. Right there, just the delta t. That's our time step. And we're also going to say that's our initial condition. We'll actually just change this name to CA naught. And this will be some concentration in the future, so I'll just change that to CA. Okay, so we have a time step, and we're going to go to CA final from a CA initial. Okay. And then if I just rearrange this, I have CA as a function of, well, my time, or delta t. I'll just put time here. If I started time 1 at 0 and then just made this equal to time, then that would be negative k times CA naught times, actually let me back up just a little bit. I'm going a little too fast. Okay, I got to take the exponentiate both sides of this expression, so I'll have exp of minus k times t times CA naught. Okay, so here's my expression, my analytic solution by separating and integrating. Okay, let's do this numerically as well. So this kind of intimidates people for whatever reason. You have to take a class on it. You learn it in the class, but then sometimes you forget it very quickly, how to integrate analytically. Also, it's really only applicable for very simple systems, one, maybe two equations. If you get any higher than that, sometimes you got to do a lot more work to be able to solve this. So I also want to show you how to do a numeric integration in Excel that can help you solve the same equation, but you're going to be approximating it. You're going to use a numeric method instead of an analytic solution, but we'll compare the two. So we're going to solve it two different ways, analytically and then also with the Euler's method. So this is a general method that can be used for differential equations, where you basically just approximate the differential term with let's say this is our initial concentration of 5, and then it's going to be decreasing as we go. We just take whatever point we're at, and we just take the last the slope right here. Okay, that helps us predict the next point. Then we take the slope, and that helps us predict the next point as well. Okay, and we do that with just a rise over run. The CA n plus 1, that just means the next time step, and this would be the current. Okay, and that would be the next. And this down at the bottom is just our delta time. And then the thing on the right hand side is just going to be equal to negative k times CA. So this is our numeric method for solving it. It works out very nicely in Excel because we can do one formula and then just drag it down. So let's open up Excel and we'll see if we can solve this equation both analytically and numerically. Okay, I'm going to put in a couple constants here. I have my C A naught, and I'll make this a little bigger. Okay, there's my CA naught, and I'll put 5 there for CA naught. My delta time. Okay, I'll just put that as delta. If I change this to symbol on the font, it'll make a nice delta there. Okay, and then I have 0.5. That's going to be seconds, and this is kilomoles per meter cubed. Okay, my K value is going to be 1, and that is an inverse second. So let's create our table here. We have time, T, and I'm just going to have, just going to express this as this plus my delta T, just so I can change that in one place, and then it's going to go ahead and just change it for all of them. So if I just drag this one down, I'm going to get my time points, and I'll go down to about 7. First of all, do 7. Okay, great. And then for my CA, and I'll do this one as my analytic solution. Now if you remember, that one was just equal to my initial concentration. Let me pull up that just so we can see that one again. Okay, there it is, and do my initial concentration times the exponent, okay, of negative k. Don't forget the F4, just give yourself the dollar signs, make it fixed, times the time, and there. And what I'm going to do now is just go ahead and double click this, and it'll drag this formula down. You can check it at different points if you want, just to see if it got the right values in there. Okay, so there's my analytic solution. Let's go ahead and do a numeric one as well. Okay, so numeric, we're going to start with a value of 5. Okay, I'm just going to put equals this value right here. That's just going to be our initial condition. And then, let's see, let's go back over here. Okay, so we're going to use this formula right here to help us calculate the numeric. This is called Euler's method, explicit Euler's method. So that's just going to be equal to, if I solve for CA n plus 1, that's my next time step, it's going to be equal to whatever on the right hand side of that expression. So that was equal to negative, I'll put some parentheses here, negative k times the prior CA value. Okay, don't put any dollar signs there because we want it to drag down. Times my delta t. Put a dollar signs there to fix that value, and then plus, and then we're going to add the prior value again. Okay, so now I'm going to fill this one down, and then we're going to see how how changing the delta t gives us different answers. Okay, makes it more or less accurate. So let's go ahead and just select this region right here, and we'll go ahead and insert a scatter plot. Okay, so there's the numeric versus the analytic solution. You can see that the analytic solution is going to be accurate to machine precision. The numeric one is going to, the solution is going to change depending on what we have for our delta t. Okay, so if we make that smaller and smaller, okay, I'm going to make this 0.5. Okay, so they're going to match up much better if I make that time step smaller. Okay, I'm going to fill this down just a little bit more, and let's do this. I'll move this plot out of the way. Let's fill it down to more time steps. Okay, I'm just going to drag all three of these down, give us some more. Okay, we'll go out to 1.9, and then I'll go ahead and just let me just go delete that plot. I can also drag, I could have just dragged that data range down as well, or it's very easy just to insert a new plot as well. Okay, so there's our the analytic versus numeric. You can calculate the difference between those two, and that would be an error of integration using the numeric method. Okay, let's change this to I'm going to come back up here, paste my plot in. Let's change this delta t and see what it does when I give it more and more values here, 0.5 or larger values. You can see there's going to be an error of integration. I'll go ahead and change the just so it doesn't scale too much here. Just go ahead and set the maximum of my x to 5, just so I'm always looking kind of at the same region as I change this delta x. And if I go to 1.0, 2, then it's going to kind of go unstable. Okay, so as you go further out, it's going to become less and less stable. Let's see if we answered all the questions here. Okay, I'll change it to 0.5 to 1.5, and then to 2.1. I'll observe, change them, and so turn that in with your answer for this problem. Okay, so that concludes this demonstration of solving differential equations. In this case, we had just a simple, this first order linear decay that's common in many applications like nuclear decay, biology, systems, a lot of others that are described by this this simple differential equation. And we solved it analytically, which is possible because it's simple, but for more complicated systems, we may have to use a numeric method. The advantage of this problem is that we can see the difference between the analytic and the numeric and be able to quantify an error exactly, and that helps us select the appropriate delta t. If I have more time points, it's going to maybe take longer to solve, especially for really large scale systems. And if I have more of these time points spread out, then it's going to calculate faster, but it might introduce some error into my numeric solution.